Hello again, method students, and welcome to part 2 of our maximums and minimums section. So a third example for us to look at here. This is one where the function is given to us, which is always nice. We're given a function n of t, which is equal to 200t e to the power of negative t, is used to model the number of bacteria present in a controlled experiment, where t is the number of minutes after the bacteria start growing, and t is an element of 0 to 10. The graph of n is shown, so not only have we got the function, we've also got a graph. Really nice, this question. Okay, part A, for what values of t is n dash of t less than 0? Right, now what this just means is, for what values of this graph here, this is our function n of t, for what values is the gradient n dash of t less than 0? So in other words, where do we have negative gradient? And you can kind of see it, right? It's just going to be everything to the right of this turning point, because the graph's just going down and down and down after that. So what we need to work out is, where is this turning point? And we can use our calculator to do that. I'm just going to mark the point, because once we get the values from the calculator, I'm going to label it. Clear all the stuff we had from the last one. All right, so the function was 200 t, we're going to put it in as 200x, times e to the power of negative t. Again, I'm just going to use x instead of t. Again, I'm a fan of doing the graphs in the main screen so that we can do some calculations while we can see the graph down the bottom. So let's drag this on. Now, as is often the case, you've got to do some work to actually find the right part of the graph. Always look for hints in the question, and a really good hint in this question is we actually have the scales on the graph here. So I'm going to change the x value so I can see from 0 to 10, or a bit extra either side, and the y value so I can see from 0 to 100. So using the window button, I'd strongly encourage you to use the window zoom rather than just hitting zoom out or zoom in. Let's make that, so x min is just a bit to the left of the x-axis, that's the y-axis, that's fine, but I want to see up to at least 10, so I might go to 15 just to see a bit extra. Y values, that's fine to start off a little bit below the x-axis there, and then the maximum, well, looks like it occurs at maybe like 70-ish, but I'm just going to go up to 100 to be absolutely sure. We hit OK, and not a perfect zoom, but a pretty good idea, and we're clearly going to be able to see where that maximum turning point is. So if we go analysis, gsolve, and then maximum, we can see the maximum occurs at 173.576. And so the question was, for what values of t, which is so 173.576, for what values of t is the gradient less than 0? Well, it's everything after t equals 1. So at t equals 1, the gradient's 0, but beyond that, it's negative. And so we can say t is an element of 1 to infinity, but we're not including that 1, okay, because the gradient is equal to 0 at 1. Okay, for what value of t is the population of bacteria decreasing most rapidly? This is a tricky question, and maybe trickier than it seems. We've just established that sort of from t equals 1, from 1 minute onwards, it's decreasing. The number of bacteria is decreasing. But at some point, and if you were to eyeball it, it looks like it's about here. At some point along the graph, the bacteria is decreasing as quickly as it can possibly decrease. It's got like the most negative gradient it has. And then gradually it starts to flatten out. It's still decreasing, but not as much, right? So somewhere in here, we've got a point that is where the gradient is most negative. That's really what this is asking. Where is the gradient most negative? In other words, what or where is the lowest value of the gradient, which is n dash of t. That's kind of what the question is asking us to do here. And so there's a couple of ways to tackle it, but probably what I would do is get the graph of the derivative and work out where that graph has a minimum. Okay, so what we mean by that is, let's take this function up the top here. Let's differentiate it, so action, calculation, diff. Right, I'll put the standard mode just because it looks a little bit nicer. So that's our derivative, and what we want to know is, where is that derivative at its lowest point? And so what I'm going to do is drag that onto the graph and have a look at the graph of the derivative. So this here is the graph of n dash t, and you can see we've got sort of positive gradient to start with. Then after t equals 1, we've got all this section where the gradient is negative, but where it's most negative is at this minimum down here. And that minimum occurs when t equals 2. Okay, so when t equals 2, the derivative, the gradient, is at its absolute smallest. It's the smallest it ever gets to. So that's where it's decreasing most rapidly. And so we could say that I guess let's just say n dash of t has a minimum when t equals 2. Right? And t equals 2 is our answer for that question. Okay, so it's one to read really carefully, because it's talking actually about the derivative and where the derivative is at its lowest, which is a little bit tricky, right? We're having to differentiate and then find a turning point for the derivative. Tough question. All right, example 4. And again, a different style of question to kind of get used to. We're told that the graph of y equals a half x squared, so this parabola here is shown below, and the point 10 is also labelled. Find the minimum distance, corrected 2 decimal places, between the curve and the point. Right, so on our graph, I'm going to label it really clearly with coordinates. We've got the point 10, and then what we're trying to find is somewhere on this curve, there's going to be a point, and you can eyeball it, you're not going to get it spot on, but roughly, there's going to be a point here-ish, I'd say, which is not very mathematical or precise, but here-ish. It's going to be a point on this curve where the curve is as close as it ever gets to the point 10, right? Where this distance is a minimum. Okay. Now, there's a couple of ways we can tackle this, but I would say a good strategy is to say, well, I don't know this point yet, but I know that I can represent any point on this curve. Remember, this curve is y equals a half x squared. Any point on this curve, I could write its coordinates as x. So I'm just going to call the x coordinate x. And the y coordinate, this seems dumb, but this is like taking your equation and subbing in x equals x. That would give you y equals a half x squared. So your y coordinate is a half x squared. Okay. Now we have a rule for the distance between 2 points, and that rule is that the distance between 2 points, I'm just going to call it d, is equal to the square root of the difference between the x values squared. So let's write the formula. x2 minus x1 squared plus y2 minus y1 squared. Right, that's our distance formula. Difference between the x values squared plus the difference between the y values squared, all of that under the square root sign. It's actually just Pythagoras' theorem applied to the Cartesian plane. So for this question, my x values are, and I'm going to call x2, let's call this one x2. So it's going to be x minus 1 all squared plus half x squared minus 0. All squared, right? And obviously I didn't need to write the minus 0, but that's just to emphasize what we've done with this formula. And so if we're trying to find the minimum distance, well, here's our rule for distance. If I want to know when that's at a minimum, I can differentiate, let it equal 0, and find the minimum. So let's say we're going to work out dx, right? Because that's what the derivative of this equation would be. Calculator question, so let's not waste time trying to do that ourselves by hand. I'm going to clear all this. Get rid of that. Alright, so let's plug in our rule. Shift power, by the way, gives you the square root template. Might save you a couple of seconds here and there on a saccharine exam. Plus, now we've got to be a little bit careful. I'm going to use the fraction template here just to make sure I can keep track of all the bits and pieces. So it's a half x squared minus 0. So I'm not going to write the minus 0 this time, in a bracket, and then that bracket's to the power of 2, so that needs to be squared as well, and all that needs to stay under the square root sign, right? So if we wanted to do this graphically, this is the graph of the distance, okay? So we can actually find the minimum graphically. I can say analysis, gsolve, and then min. Again though, anything that's on the graph screen here is only going to be a decimal value. It won't give us exact values, and that might be a problem in certain questions where we have to find exact values. This one says corrected 2 decimal places, so we're actually okay to just use the value from the graph. So from the graph, we can see that the minimum distance is occurring when x equals 0.77, and the minimum distance is 0.375 units. If we need to show some working out, like we did before, what we might do is go, well, let's actually write down the derivative. So let's differentiate the rule. It's a horrible looking thing, but it's not too bad because we can just write it down. We're just copying it. So the derivative is x cubed plus 2x minus 2 all over the square root of x to the 4 plus 4x to the 2 minus 8x plus 4. Right, we let that equal 0 and we solve it. Right, well, we solve it, calculator solves it. Action advanced solve, 0 equals that guy. So make the most of copying and pasting here. You don't really want to type messy expressions in over and over again. And, all right, good thing we didn't have to write down the exact answer because that looks grim. Let's pop it in decimal mode, and there we go, there's our 0.77. So the same value that we found on the graph, just good to, I guess, be sure. So the minimum distance occurs when x equals 0.77. Now, the question said, and this is why I always come back to the question, find the minimum distance. So what we've found at the moment is the value of x where the distance is minimized, but we haven't found the minimum distance yet. So what I'm going to do here is go, all right, well, x is equal to 0.7709 and so on, but the minimum distance means I need to sub that x value back into the distance rule. Okay, and so again we can kind of use some copy pasting here. that was my original function. So I copy the bit before I hit differentiate. Let's scroll down, come on. There we go. And keyboard math 3, given that x equals this number, I'm going to copy all of it so my answer is as accurate as it can be. And there's our minimum distance, again, that we saw from the graph. So probably what I'm learning about showing you both ways here is that for this particular question, the graph method was probably quicker. But again, this way lets you show more working out if it's a 3-mark question or something like that, where you've got to show steps. And so the minimum distance, corrected 2 decimal places, would be 0.38. All right, so let's say we're going kind of over here, but when x equals 0.77 and the rest, the distance equals 0.38. We don't really have units here because we're just working on the Cartesian plane, so we're not going to say centimetres or metres or anything like that. It's just a distance of 0.38 units. All right, a couple more application questions and a few more tricks to sort of see. As always, the more tricks you see, the less likely you are to be surprised when it comes to a SAC or exam question. So keep up the practice and chat to your teachers if you need any help. Bye for now.